right, welcome to the average atomic mass review session. We're going to go through two problems that dealing with average atomic mass. They should look familiar to you from Regents chemistry. So as a reminder, what is average atomic mass? It's the weighted average of all naturally occurring isotopes of an element. Now, the important thing with average atomic mass is this is not a regular average, it is a weighted average, which means that we have to take into account the fact that certain isotopes occur more frequently than others and weight the average mass towards those more frequently occurring isotopes. That means that you take the percent into abundance. If, in terms of calculating average atomic mass, hopefully this looks familiar to you. You take the mass of an isotope and you multiply it by the percent that that isotope exists in nature, and then you divide by 100. You do the same thing for any other isotopes that occur, mass of that particular isotope times the percent that that particular isotope occurs, divide by 100. If there's more than two isotopes, you just continue doing it for all of them, and then you add everything together. There is no final dividing by 2 or dividing by 3. By multiplying the mass times the percent, that's how you're taking the average. That's what a weighted average is. Now, this is how I teach it in Regents chemistry. You might also have seen turning the percent into a decimal. So 25% will become 0.25. That's what the dividing by 100 is accomplishing. So looking at some sample problems. 3 isotopes of silicon occur in nature: silicon 28, silicon 29, silicon and silicon 30. Calculate the average atomic mass of silicon. So what we're going to do is we're going to take the mass of each individual silicon, multiply it times the percent, divide by 100, add everything together. That's going to be the average atomic mass. A point here, though, if you'll notice for silicon 28, they give us the mass, obviously, in the upper left-hand corner, 28 right there, but then it also gives us a more detailed mass. We want to use this one. We don't want to use that one. We've got more information than just the 28, so we're going to use the one that goes out to 5 decimal places. So the mass of the first isotope, 27.97693 times the percent. The first isotope has a percent occurrence of 92.21. Then we're going to divide this whole thing by 100. To that, we're going to add the same thing for the other isotopes of silicon. Again, we don't want to use 29. We want to use 28.97659. We've got more information. Let's use the one that's more accurate. We're going to multiply it by the percent of this second isotope, the 4.70%, saying this one occurs 4.70% of the time. Divide by 100. And we have a third isotope, so we're just going to do this one more time. The silicon 30, so 29.97376 times the percent that this occurs, 3.09% of the time, divide by 100. And then that's going to give us our answer. Just this, the first isotope information, second isotope information, third isotope information. When you do that math out, and I would recommend actually writing down what you get after you do this, you should get an answer of 28.0856. Unit is AMU, atomic mass unit, and you'll notice that this is closest to silicon 28. It means that, okay, silicon 28 occurs 92% of the time, so it makes sense that the weighted average be closest to that particular value, and it is. And then one other problem. Element X has an average atomic mass of 153.77 AMU and 2 naturally occurring isotopes. One isotope of element X has an atomic mass of 152.375, the other has an atomic mass of 154.699. Determine the percent abundance of the 2 isotopes of element X. Now, you might not have seen this type of problem in Regents chemistry, but it's still the same type of problem. What we're looking for is percent abundance rather than average atomic mass. So let's call the percent of element of X1, the first isotope of element X. Let's say that that's X. Let's assign that X. Well, what's the percent for the other isotope going to be? Here's where a lot of students want to say it's Y. that the percent for the first one is x and the second one is y. That's not going to help us because we are only going to have one equation here. And as you know, you can't solve for two unknowns with one equation. Guys, there are two percents here. If one of them is x, the other one has to be 100 minus x. Right? If one percentage is 25, there are two things. The other percentage has got to be 75, etc., etc. So by doing this, we can now essentially solve the problem. In fact, I'm going to say in terms of decimals instead of percents, it's going to be x and 1 minus x. Essentially, all I'm doing here is dividing by 100. It'll make the work a little bit easier. So now we're going to set up the same thing, only now I know that the average atomic mass, 153.77, is equal to the weighted average of the two isotopes. So the mass of isotope 1, this is average atomic mass, is equal to the mass of isotope 1, 152.375 times the percent. We don't know what the percent is, so we're going to put in x here. The average atomic mass, 153.77, is equal to the mass of isotope 1 times its percentage plus the mass of isotope 2, 154.699, times its percentage. Now here's where if you're putting in y, you would get into trouble, but we know it's not y. We know it's going to be 100 minus x in terms of percent, in terms of a decimal, which will make the work a little bit easier here. 1 minus x. This now becomes a problem that you can solve. This is an algebra problem. You can get the answer here. So just simplifying a little bit, 152.375x plus 154.69, distributing this 154.69 to the 1 minus x, minus the 154.69x. You can solve this. You've got one unknown. You want to group the x's together, group the integer, not the integer values, the variable values together. When you solve these, you get a value for x of 0.3997. You should make sure you actually go through this math and you get the same values as I did. So what does this mean? Remember, we said we're working off of this assumption here that the decimal for the first one is x and the second one is 1 minus x. So in terms of a percentage, this is 39.97%. This is for isotope 1. This one, right? That's what we assigned it, the 152.375. Now it's easy. What's the percentage for the other isotope going to be? 100 minus that value. So if we do 100 minus 39.97, we get 60.03% for isotope 2. This one. And so that way, if we don't have two, if it asks for percent abundance and it gives you two things, you don't plug in x and y, you plug in x and 100 minus x, or 1 minus x. And that's how we do average atomic mass problems.